So welcome everybody. My name is Samantha Rhodes. I'm one of the co-organizers of Roger That, and also I'm the professor of engineering. We have our last speaker is Amanda Stark, and she has a truly STEAM background. Amanda has a Master of Fine Arts degree from Bowling Green State University in 3D fine art and metalsmithing. And then she came to Grand Valley, so she's one of ours. She's a Laker for a lifetime, and she got her bachelor's degree in product design and manufacturing engineering. So woot woot to PDM, to the PDM folks, back in 2016. And then she got her master's in mechanical engineering from Old Dominion University in 2020. She completed an internship at NASA in 2015, and for the past 9 years has been an engineer at NASA's Langley Research Center. And she will be talking to us about her work on the MARVL project. And I have completely missed the opportunity for a Stark MARVL joke here. So insert your own joke at this point. Take it away, Amanda.
All right. Well, thank you so much for that introduction, Dr. Rhodes. I'm going to warn everyone, if you heard it before the recording started, I am getting over being ill, and I have this lingering cough that just won't leave me alone. And sometimes my voice starts to get a little kind of scratchy sound. So hopefully I don't have a problem with it, but I might have to take a break at some point, just to let you know. Let's see how it goes. As Dr. Rhodes said, I will be talking about a little bit about Mars transit, since I know the whole conference is looking at time. And then I will be talking about what my project is that I'm currently leading, which is called MARVL, what we're doing, what we're working on. And MARVL is an acronym. It stands for Modular Assembled Radiators for Nuclear Electric Propulsion Vehicles, because here at NASA, we love our acronyms. All right. So I'm going to start by talking a little about time to travel around the solar system, then nuclear electric propulsion for Mars transit. Is that actually possible? I'm going to go over some basics for heat transfer, since that's actually my background here at NASA. And then I'll talk about what we're working on with our MARVL project. And then I'll kind of do just a short little tiny closeout. So how long does it take to get to Mars? Well, if you are on a commercial aircraft going 560 miles per hour, it will take 19 years to get from Earth to the sun, 9.9 years to get to Mars when it is at the closest point to us, and then 774 years to get to Pluto. Based on this, we are very lucky to have other forms of transportation to get us around the solar system. But you can imagine, if you have taken a trip to Europe or even across the United States, what it feels like to actually be on an airplane for even just those handful of hours. So that's kind of a long time, really. So now Apollo 8 has the shortest travel time to the moon, with it being just under 3 days. Getting to Mars, we have non-human missions that have taken 201 days as the shortest, with the Mars Exploration Rover Opportunity in 2003. And then the longest being Viking 2 orbiter in 1975 at 333 days. We also have a more recent mission, which is the Mars Orbiter mission in 2013 that took 322 days. So just kind of some ideas of current missions, how long it's taken to get to Mars. Then if you want to get to Jupiter, we're looking at 5 to 6 years. So still kind of long. Now, taking almost a year to get to Mars, maybe it's not all that bad, since those astronauts will be the first to see Mars, as long as they can survive the trip. And I know some will say, sure, why not? I'll do it. And they just might be the first. When you're actually looking at traveling to Mars, there's a lot to consider. Planet orientation is a big one. Earth and Mars do not have their orbits on the same plane. There are also alignment considerations that will dictate the duration of the mission. I have to admit, I am not an expert in orbital mechanics, but there are people who are, and they have several trajectories that are possibilities. Here, I'm actually presenting two major ones that are actually being considered. The first is the conjunction trajectory concept, which is found on the left, while the second is the opposition trajectory on the right. They get their names from the location of Mars in relationship to the Earth. Actually, I'm going to pull up my little laser pointer. The conjunction mission will give you a longer time on the Martian surface, but the total mission duration is over 1,000 days. The opposition mission will have a much shorter duration on the surface, and will be a shorter overall duration, and will give you a Venus flyby either on the way there or on the way back. I have it shown here, I think, on the way back, if you look closely at it. Now, the travel time will vary depending on your spacecraft, and that is why I don't actually have any travel durations on this slide here. And these orbital alignments happen around every 26 to 28 months. So right now, we are looking at a potential opposition class Mars mission around 2038, because this also gives us time to develop the technology that we're going to need. Now, talking about the technology we need, the big one is how we're going to get there. Currently, there are several options that are under consideration, but all really need more development. Right now, there are engineers looking at traditional chemical propellant, so that's the kind of rockets we use right now. There's electrical propulsion, both solar and nuclear thermal propulsion. I can't go into a great deal about a lot of these, but I can actually talk a little bit more about the nuclear electric propulsion than the rest, since that's the area I'm actually working in. But there are some concerns with traditional propellant when looking at the required amount of propellant and the mass, because mass is a big factor when you get to space travel. You want to do whatever you can possible to get the mass as low as you can. When looking at solar electric, you need to start to wonder what happens as you start to move away from the sun, since that is usually using the solar flux to generate the electricity. Then for nuclear thermal, you are using a nuclear reactor to heat your propellant to generate the thrust. And there's a lot of technical difficulties that go along with it. Now, the other one I have here is this question about how about a nuclear electric propulsion, nuclear thermal hybrid, since most of the time nuclear electric propulsion will have a chemical propulsion assist. And I'll actually talk about that just a little bit later. There is also something else that needs to be considered for every mission, and that is galactic cosmic rays and solar particle events. Both of these lead to having more shielding so that the human body can survive the space travel. So that does cause an increase in mass. And unfortunately, then it goes on to this process of you need more mass, you need more propellant, but then you need more propellant, then you need more mass. And it's kind of this, loop kind of situation you end up in. This is the fun part, because this is the nuclear electric propulsion chemical vehicle hybrid. I love it. So there are 5 major subsystems to the nuclear electric propulsion vehicle. You find your reactor down here at this end, and it actually has its own coolant system that then connects to the power conversion subsystem. The power conversion subsystem is what is actually generating the electricity that travels down this truss through the power management and distribution subsystem to both your electric propulsion subsystem located here. So this is where your propellant, your thrust comes from. Then it also goes all the way down to back here where you have these kind of modular units, where this is where your crew or your cargo will be located at for your mission. Now, along this truss as well, there's also a very long fluid loop that's moving waste heat to the primary heat rejection subsystem. And these are very large radiator arrays. This is the part that I actually work in, since I'm a thermal engineer. Then back here, you have your liquid oxygen methane chemical propellant stage. Now, that chemical propellant stage is there to get you out of the Earth-Moon system, to get away from Mars, and for the Venus flyby. So any place you have a gravity well, you need to escape from. The nuclear electric propulsion system doesn't have that thrust that you need to get away from that gravity well. So the chemical system is there to actually do that. And this is where people start asking, well, can we replace that chemical system with a nuclear thermal system? And then that way, that generates the thrust that's needed to get out of the gravity wells. Okay, I'm going to talk a little bit about heat rejection, since this is the work that I've actually been working on since 2017, and also what I do when I'm not actually working MARVL. So I'm going to go into some basics of heat rejection, and I think we can agree that a simple definition of heat rejection is the process of transferring heat from something to an environment. Very basic. A good example is an electronic device. It uses the atmosphere to maintain its components at a healthy temperature. It may use fans or heat pipes to expel the waste heat to the surrounding air. This is known as convection. The image here, this little guy right here, is of an off-the-shelf component used in the SCALPS mission, photographed with an IR camera. So this is the actual component. That's a visual picture of it. It's 2 inches by 1.5, so you can see it's just a little tiny guy. This is 63.6 degrees Celsius, so it can get very hot, and this is an atmosphere. Now, when you place an electronic device in space, what can happen? Well, we know space is cold, but if your electronic generates a lot of heat and you place them inside of a spacecraft without an atmosphere, they might overheat because you don't have that atmosphere to help cool it. You can move that thermal energy around within the spacecraft, and maybe you have some components that actually do need to get heated up more because of how they perform. But sometimes you just have too much. You need to get rid of it. And in order to do that, you want to use radiators and actually radiate it out into space. So deep space is really cold. And the NEP vehicle will require 2 megawatts of electricity. And to give you an idea of scale, that will power about 1,000 to 2,500 homes, depending on usage. It's a lot. But along with the electrical power, there's 4 megawatts of thermal waste heat. And in that case, that's why we need those very large radiators to remove that, because we just can't do anything with all of that waste heat. How it works is that there is a fluid that will transport the waste heat from the power conversion subsystem. And hopefully you can see my pointer, right? Uh-oh.
Yes, it's coming through.
Okay, good. All right.
Sorry, yes, we can see your pointer. Yes.
I didn't want to be pointing at stuff and also people going, what is she talking about? So, okay. Yeah. So you have a fluid that transports the waste heat from your power conversion subsystem down to your radiator panels. Inside the panels, you have heat pipes that then transfer that heat, that thermal waste heat, away from the fluid and then distributes it across this radiator surface. That radiator surface then goes and looks at deep space, and the waste heat will be radiated off into that deep space. All right, on the other slide, I talked about heat pipes. Heat pipes are a very interesting passive heat transfer system. You take a fluid and place it in a vacuum with a wicking internal surface. So you can see over here, we have this vacuum cavity with a wick surface around it. This is a cross section of that. Then you heat it at one end, and right here in this part. Your fluid will take the thermal energy and change into a vapor. That vapor will travel along to the cold end, where it will condense and release the thermal energy to the wall. The wick will then allow the liquid to transport back to the hot end, where it will go through the whole process again and again and over and over and over until you actually remove the heat. Now you can place the radiator panel face sheet at the cold end, and it gives you a nice large surface area that can move the waste heat into space. So that's how we radiate it off into space. I include this image here just so we can have an idea of something that's similar. The International Space Station has an environmental control system that uses radiators to keep the internal temperature comfortable for everything on board. Now, with the electronics in there, the air can actually heat up pretty easily. So there needs to be a way to get rid of all of that heat that's being generated by the astronauts and those electronics. In this picture, the radiators, as a reminder, are just inside these orange blocks here, and there's a couple back here as well. These large vertical surfaces are actually the solar arrays. So those are generating the power for the International Space Station. What the International Space Station needs is about 1,300 square meters of radiator area in order to keep the internal temperature comfortable for everyone on board. Now, if we compare that to what is needed for NEP, it gets really interesting. I figure the best way to get an understanding was to compare this to a football field, since that's something that everyone can kind of relate to. My Mars versus Earth field is proportional to an actual football field. And on the right, this side over here, we have the 1,300 square meters for the ISS. And on the left is what we need for the NEP vehicle, which is around 3,000 square meters. Actually, it's a little bit more than that, we're finding. Now, the nice thing is that the space radiators are double-sided, so you can kind of fold this in half to get an idea of what the size of the radiators are. But compared to a football field, still a third of a football field, still pretty big. So that's kind of what we're looking at for the size of these. Oh, okay. I'm going to first point out that I am not in thermodynamics, because thermodynamics is very different than heat transfer, but a part of me is very happy for that as well. And I'm going to talk here a little bit, since the observant people probably noticed on a previous slide that I had mentioned that the power conversion subsystem could be a Brayton engine. This is one of two options, where the second is a Stirling engine. Our stakeholders have advised us to look at the Brayton engine as the power conversion subsystem. And I'm not going to go into much details about this, because like I said, thermodynamics is not my thing, I guess I'll say. But the Brayton engine can generate power by using the heated fluid in a turbine connected to a generator. In the NEP vehicle, the fluid is heated by the nuclear reactor. This process generates the waste heat. And that's all I'm going to say, because I'm not going to go into much detail about this. But I will mention it later on as well. So I kind of wanted to just touch on it just briefly. Okay. This gets us to the work that I've done on a regular basis since 2017. So thermal engineering is what I do most of the time. And a big part of thermal engineering is actually doing thermal analysis work. A thermal engineer will take and look at a space system and evaluate the system to make sure that there are no thermal issues during all of the stages of the mission. This can include hand calculations for specific components, research into operation and storage temperature limits, building thermal models and specialty software, and thermal hardware testing. That last one is my favorite. When thermal modeling, you include the space environment, and in most projects, the full mission will not be actually included in the whole thermal model. Instead, what we do is we look at key locations in the mission where we'll experience maximum and minimum temperatures, and that is what we actually put into our thermal model. So we're not running huge, long, 3-year-long missions within our thermal model. We're only looking at small subsections of it and making sure that everything within those, that's going to be healthy there, because everything else will fall in between. The extremes, we'll say. Then the results from this thermal modeling will go and lead to testing conditions for hardware that's actually bound for space. And down here at the bottom, I'd like to point out too that for the MARVL project, we're developing technology for a crewed NEP Mars opposition class mission, which is with a departure date of 2039, and we're looking at a total duration of about 3 years for that mission. All right, the process for analysis work involves building the thermal model, placing the model in an environment of interest, and then collecting the results. This work presented here was actually done by one of our MARVL interns last summer, and he built the full NEP vehicle in a software called Thermal Desktop. That program has the ability to set up orbital parameters so that the spacecraft can be placed in a variety of orbits and locations. He then collected the results for the individual radar panels and presented them in this final format here. So this here is our full thermal model. The full spacecraft, you can see it's all kind of boxy because there's lots of details for thermal we don't really need. Then he placed it in this Martian orbit that's here. And then he took the data and he actually laid it out so that each one of these little blocks is actually one of these radiator panels that you see on the surface here. And then our output actually shows that we have some type of response that's coming from the center section here. That's why it actually looks like it's a warmer temperature there. So that's something that we need to pay attention to when we're actually designing our radiator panels. Then for MARVL, we had another intern use a radiator panel to identify the 6 worst case hot and cold mission locations for when the reactor is powered on and off. She actually used this little panel here that's kind of just looks like it's floating out in space. I'd like to point out that the location where the reactor is off is only while near Earth, since the assumption is that once the reactor is turned on, it'll stay on until it needs to actually get refueled, which is going to probably be several Mars missions. It's not just going to be one and done. This is going to be a reusable vehicle. Excuse me about that. And then when the reactor is powered on, we find that our maximum and minimum cases are either found at Mars or interplanetary space. So these two are both Martian orbits, where this one is actually an interplanetary space for actual minimum temperature. Now, these locations will actually go and travel through with the rest of the project. And every time we need to do some thermal analysis work on a component or the full system, we'll be using these as our kind of bounding cases. All right, now I'm going to go into the details about MARVL. The Modular Assembled Radiators for NEP VehicLes, or the MARVL project, is an early career initiative project that is funded by NASA's Space Technology Mission Directorate. The ECI program is an opportunity for early career engineers and researchers to lead their own project that consists of a team of early career individuals. These projects receive funding for a 2-year time period so that the scope, schedule, and budget needs to fit within these restrictions. Early career is usually, it's defined differently depending on what center you are in. At Langley, you are early career if you were in your first 10 years since your last degree. So I'm actually still at early career somehow. Another requirement is that you have to have an external partner, either in the private industry or academics. This gives us the opportunity to actually go and engage with other folks outside of the government, since, well, private industry academics do behave and perform differently and have different areas of topics they cover than what government can actually do. And as I'm something to point out here, we actually started in October 2024 with this project. That's when we received what's called our authority to proceed. And sadly, we will be ending at the end of September this year. And I think we'll actually find that we're rather successful when we get there. I just have to show my amazing team, because this is the team I'm working with and they are phenomenal. The team consists of members at several different NASA centers, depending on their technical expertise, because the one thing you find is there are a handful of different centers and Each one really has their own specialty area that they really focus on. And so having those people that actually can get the connections they need for the mentors in the background is crucial for the success of a project. Okay, what MARVL is doing is it's looking at incorporating in-space assembly into the design of the primary heat rejection subsystems of the very large radiator arrays, we call it the PHRS, of the NEP vehicle. A lot of the current studies of NEP Mars transit vehicles uses the quad wing configuration, which is found here on the left. So that's this one over here where you have your radiator arrays are in the shape of an X. This concept is dependent on the radiator arrays, truss structure, power conversion subsystem, and reactor to be folded up so that it fits into one launch vehicle. So if you think of the James Webb Telescope, it's something along those lines where this massive part of the vehicle is going to get all folded up and launched on one launch vehicle. Now, there's a lot of questions of whether it's going to happen because there's a lot of mass there, and there's even the question of can SLS actually deliver the system to space? If we can actually go and switch the design to a bi-wing design, which is this one, which just has the radiators as a flat sheet, then we find out that we can actually break that large radiator unit into modular units, and we can assemble it with using robotic agents in space. The bi-wing design can lead to a good number of advantages for the system. And one of those advantages is actually from the thermal performance point of view. With radiation, you have what's called a view factor. If a surface can see another surface, then both surfaces will affect the radiation of both surfaces. If you look to the right here, this far right side right here, you will see that there is a comparison between the two configurations. The quad wing requires more surface area because the radiator panels see each other and will affect the radiation efficiency of each other because of that. Then also you do have this solar vector that's here, which is what you see of the sun hitting those surfaces and heating them up and almost like negating the fact that you need to radiate that temperature out. So if we switch to this bi-wing concept, the radiator surfaces don't see each other anymore. You can fly edge onto that solar vector, and then that way you get the most efficiency out of your radiators by looking to deep space. So this system has the potential of expelling a much greater amount of system based off a surface area than this system here. You have to increase your surface area, which is going to increase your mass. So this could be a very much more efficient system. Okay, let's see. Hopefully my video is running. Now, the next part is the in-space assembly process. We are looking at using robotics to assemble modular units in space. At Langley, there's a whole team that's dedicated to the research of how to build large structures in space, since there's a lot of advantages to using robots. This video is from the PASS project, and their goal is to build the support structure for a large-scale telescope out of these elements made of lightweight rods. To give you a scale, those are actually tables that they have back there. And then there's that guardrail that's back there, and that is at waist height. So this is quite a large robotic arm, and these components are quite large when you see them in the lab. While in-space assembly can take advantage of reducing risk to astronauts, build larger structures that can actually fit in a launch vehicle. It can lead to reducing mass. There's a possibility of repair and replace if something is damaged, and it gives us a more flexibility in the design process. With MARVL and the NEP vehicle, we're only looking at part of the primary heat rejection subsystem, or PHRS, as I said before. I point out that this subsystem is a very large radiator array, and when you look at the whole vehicle, it ends up being 40 to 60% of the total dry mass of the vehicle. That's a good amount of it. But the MARVL team is only looking at one system of interest within the subsystem. The PHRS has three key functions. It accepts the waste heat, then transports the waste heat, and then radiatively rejects the heat to space. MARVL is only looking at part of the fluid loop, the interface between the fluid loop and the radiator panels, and then the radiator panels themselves. So this little dotted line is enclosing our system of interest. We have this fluid loop that comes through here. The pump is outside, but we have an interface here, and then each of our radiator panels. So there still is the pump, a long trunk line because it has to go all the way down this whole section here, and then a power exchanger at the power conversion subsystem. So those are out of our scope. We're making the project much more smaller, keeping the scope smaller, so that way we can actually be more successful with our development. I added the slide for all the engineers out there so you can see what our success kind of criteria is. So once we identified all of our systems of interest, we then went and looked at our needs, goals, objectives, and success criteria. And with that, we also pointed out what our key performance parameter is. This metric we can actually use to determine how successful our project has actually become. So that's one thing we're working on, is making sure we get this KPP to our goal of 3.5. I'd also like to point out too that there are a lot of different requirements that we've actually had to follow for this as well, and we're keeping a kind of a running list at each different level of what those requirements are as well. Our objectives on that previous slide then dictated to us our critical technology elements, and this is where the technology development is actually taking place. These CTEs give us buckets that identified where the technical work is needed and has helped us stay focused on the scope of the project, so that way we don't actually are going off to different areas and finding more other fun things to do. Now, the numbers here are just identifiers. There's really no priority. Our CTE1 is our integrated simulation framework. With this, you can think of it as a very, very low level digital twin. If you remember back to the video I showed of the robotic assembly operation, that is what this will look like, and it is essential to verify that the assembly process will work with our design. CTE2 is our radiator design. This needs to be both functional from a heat rejection point of view, fit into the current launch fairings, but also be designed to be manipulated by robotics, because we want to make sure that we can actually move these around with robotics while in space. CTE3 is our high temperature fluid interface, and this is the components that will actually hold everything together when it's assembled in space, but it also has to allow for liquid metal to flow through without leaking. And right now the team is actually working what that modular unit will look like and where those interfaces will actually be placed. This is a massive system, so we are breaking it up into smaller units to make it a little bit more easy for us to design. This helps with the design process, but also adds redundancy to the system. We have been advised to design so that the vehicle has 4 Brayton engines. This allows our system to have independent radiator wings for each Brayton. It allows the system to be divided into 4, which will lead to a more modular system when you actually can take out one Brayton and have its own radiator set that will actually keep it operational. Then from there, we take and we break the wings into individual arrays, which is what you see in the center here. So we have a wing that then goes to an array. And then from there, we can take and look at the individual radiator panels along the array here. In this picture here, this black line is our trunk line, which is moving the fluid with the waste heat down to our arrays here. And then once you get to this point here, there's this yellow chunk down the middle here, and that is actually more fluid loop lines. It's been simplified in this image because it gets really messy, but we also don't have the heat pipes that are listed on here. This center part here will also have micrometeoroid orbital debris shielding, so that way while it's in low Earth orbit, we don't have a problem with getting a space debris or a meteoroid to actually go and hit that fluid line and cause a huge hole, and then we lose all of our fluid. That's what that shielding is there for. And then also, each of these have a number and a letter on them, because as you move away from the hot part of the fluid and you move out this way, you'll see a decrease in the working fluid. There's a return line that brings a cooler fluid back. So as you move away, the fluid is cooler. You need different heat pipe configurations to expel that waste heat. It can't all be the same when you have a hot temperature versus a cooler temperature. So that's what those are indicating. All right, so the previous image did not include heat pipes. I added that here. The heat pipes are sandwiched between face sheets and are also embedded in the fluid loop. So this is our sandwich here. So it's the cross-sectional area right here. You can see face sheet, and then you have a heat pipe with a little bit of foam saddle that holds it in place. And this here is the heat pipe embedded into the fluid loop right here. So this red line that kind of zigzags back and forth, that is our fluid loop. We have an inlet temperature of 550 K, and that's about 530 degrees Fahrenheit. So we're using Kelvin for our measurements for temperature. And then our output temperature is 330 Kelvin, which gives you about 130 degrees Fahrenheit to, for all you bakers out there or cooks that are here. So for radiators, this is considered hot. Usually we're not seeing temperatures that are this high when we want to radiate temperature, when we want to radiate heat, thermal energy away. Now, the fun thing that we had to do with the whole MARVL system, we had to identify some terminology so that we could actually converse about what we were working on, because you talk about radiator panel versus array versus panel set, and things get confusing. So this image over here is kind of our key for our radiator terminology. We revisit this every once in a while when we feel like there is something that needs to get modified as the actual design progresses. The last major technical element that we are working on is our high temperature fluid interface. I wish I could have showed you some actual designs of it, but we actually are seeing that we're going to be able to pursue a patent, so I can't actually do that here. But I can actually do a similarity. So this will actually be, excuse me, this is actually going to have, if you look at this low force quick disconnect, that is for a cryogenic surface. You can think of this as those connectors that you just push them together and they make a connection, you can pop them apart. So that's the quick disconnect part of it. So we're looking at actually using that quick disconnect kind of design, so that way when it's apart, we don't have our fluid leaking out. But then as soon as it engages, it allows the fluid flow. This will allow for actually repair and replacement opportunities later in the future, and plus will be a little bit easier to connect. Now ours will actually have a larger plate that runs around where these kind of flanges are here. There'll be two of them as well, since we have an out and an inline. But also that plate will hold a mechanical device that will actually hold everything together. And it also will have the robotic interaction mechanisms included as well. So that will be the connection that will hold everything together. On this left-hand side here, we have a potential modular unit that we're actually talking about. So this will be the item that the robots will be moving around in space. And to give you an idea, and I apologize for leaving the dimensions off here, but this is 2.5 by 1. So you can see how big that's going to be, about 7.5 meters or so by about 4 or 5. Now, the other thing that is missing in this design too, you're probably going, how is that fluid loop line going to hold everything together? That's the other part that's missing. That's what we're working on right now. So we have our fluid loop running down the middle here. Our blue line is the return line, but there's no structure. So we're working on actually looking at what that structure needs to look like in order to survive mission loads, and also the loads that we're seeing that the system is applying on itself. With our work, our goal is to get ahead by producing a design to support the NEP Mars transit vehicle. Like we were talking about at the beginning, I'm actually working on Artemis, so I'm going to the next step and trying to help us figure out how we will get things, people, whatever we want to Mars. So that's what we're pretty much doing here. This work is very exciting. I actually really enjoy it a lot, along with the thermal work I've been doing. I have been very grateful for the opportunity to present here today, and I hope everyone has enjoyed it. And this concludes my presentation. So thank you for attending, and I can take your questions now.
Thank you, Amanda. I just wrote down, somewhere your thermofluids professor is wiping away tears of joy. Because this is excellent. This is so technical. And I scribbled down a lot of questions, and I'm sure that there are people who have more questions. So please feel free to put them in the chat. You can send them to me or to Dina. But I did want to start with a question actually that was sent, and then I had like a bit of that same question here. But you talked about in-space assembly for these panels. And one of the questions was, do you see in-space assembly using robotics as replacing astronauts, or working alongside them? And my question was, do you see in-space assembly as being the way to go, or now that we're going to the moon, can there be lunar assembly? Is that one of the things? So I sort of put both those questions together for you to answer.
The answer is yes.
Yes. Okay.
So because right now there's a lot of talk about autonomous, and is there a way to have robots go and do autonomous checking of systems, so that way we don't have to have humans going to check something out and have all that risk involved with human lives, if a robot can just do it. So like you think of the Hubble Space Telescope, where it had to have some updates. What would happen if we actually had robotics that were set up to go and do that? Right. Would it be quicker? Would it be easier? We wouldn't have to worry about the people involved. So that's why I say yes. And there also is projects, like I have folks I work with that are actually looking at, hey, how can we do, building on the lunar surface with robots? What does that look like? What can we do? Can we use the regolith? Can we actually build structures and then fill that up with regolith to actually have it be a support structure? So that's why I say yes, because it's all kind of across the board. Yeah.
Well, and then there's also the I don't know if you saw the video of those robots in China, the humanoid robots, and if they can dance and do karate, I think they can do some
exactly.
thing together of structures. That's amazing.
So
yeah. Go
And
ahead.
then with that too, there's also a lot of teams that are saying, how can we help the astronauts out? Because we know the science research, you don't want your robots to doing that. Let's not have AI go there yet. We want to get the people there so they start actually doing that research. But if they have robotics to help them, then that might expedite things, because moving around those big spacesuits out in a space environment isn't the easiest thing, I don't think. I haven't done it myself, but I would think it would be. So,
Right.
yeah.
Okay, and then another question that was asked in the chat was, most of the general public doesn't really know anything about thermal systems, but they might really impose a limit on deep space exploration. Do you think thermal engineering deserves more attention in the way spaceflight is discussed, particularly in journalism and other public-facing communication?
Yeah, I would agree with that, because I from my point of view, coming to NASA, I did not realize how important like thermal is for even electronic systems, because we have such a great advantage with our atmosphere. But then once you put something in a vacuum and it needs to actually produce data or do calculations, then suddenly you got to do something to make sure the heat doesn't destroy it pretty much. So yeah, thermal engineering is I see being very crucial, and I would agree. Yes, there needs to be more emphasis put on it for sure. So.
Did you do some of this, like some of the stuff that you're using right now? Did you do it during your bachelor's, or are you drawing on more of your work during your master's? And kind of
I will
bit of
say
both?
that. So when I was at Grand Valley with the co-op, I actually did 2 co-op sessions at NASA, and that's how I started realizing, oh my gosh, this thermal stuff is really interesting and it's really important. So a lot of the specifics that we have to deal with, we learn it on our job, but having that background knowledge of heat transfer, and like I said, thermodynamics, not so much, because that's a whole other area, but having that background knowledge of heat transfer was actually very critical for me. So yeah.
Nice. And then you were talking about how the whole, so I'm going to go back to the top because I've written questions. So going back to the start of your talk, you talked about just keeping the mass low, right?
Yep.
Is there kind of a magic number that you're looking at that you want to stay under?
So I know with our KPP, we do have that for the nuclear propulsion vehicle. And there's, because the lower we can get that, the more efficient the vehicle could be. And then, of course, the more efficient the vehicle could be, you can actually, adjust the mass kind of thing. So we do have that kind of driving factor with our key performance parameter for that.
Yeah. And then is it sort of, do you measure it in terms of, because I trying to think of other massive objects in space right now and are man-made, like, is it like 2 times the Hubble or 2 times James Webb or something like that?
It all depends on the system and what your goal is, pretty much. So like, if you look at the International Space Station, that's kind of the first thing we can kind of say that was assembled in space. And all of those modular units had to fit in some launch vehicle. And at that point, we did have oh gosh, it just left my mind, the shuttle to actually help us with its large cargo bay. So in that case, all those modules were based off of what the shuttle could launch or whatever the next rocket was that helped with that. So you have to kind of keep that in mind of what that can actually support as well. So
and now there are companies that are looking at doing even production on the moon, right? So you could actually have, that's pretty sort of sci-fi.
It also with MS too, if you think back to the video I showed where it had all those rods are actually just rods that they can go and put them together, build that kind of structure. Then they have the robots go and put that structure together. So if you think, if those are carbon fiber and you stack them all up in a bin, that's a lot you can move. So in that case, the mass is already pretty low because of carbon fiber. And then you have a lot of them and you can build a pretty massive structure with that.
And then I had a question about you. Whoops. I had a question about you sort of radiating the heat into outer space to get rid of it. Was there any thought about recycling that and making that useful and, using that heat for a certain purpose?
So there's a certain amount of you can, and there are people talking about, hey, let's recycle it into the habitation, but it is so much that you can't even do that with it. You don't even need all of that. And that's one reason why we got to rate. And there are people saying, what can we do with this? Is there something we can use? Can we add another power system on? If you do that, then suddenly you have more waste heat you're generating. So
Well, I'm just going to give
they're
everybody a
working on
sneak
it.
peek that we have our astronaut behind me because I'm using
It's
her
okay.
green room, and she's actually been on the space station. So come see
Nice.
him.
There you go. All
Okay,
right.
so that's the other thing I was going to get at is that you have this fluid at a really 550 K. That's
Mhm.
the kind, and then outer space is how cold? Like
Um,
super cold.
yeah, I'm trying to think. I think it's like negative 270. Is that right?
Yeah, is that
I don't
Kelvin?
want to get mixed up between Kelvin and Celsius.
Yeah,
And I'm like, I know
yeah.
they're the same there pretty
Yeah.
much, but I think it's like negative 270 or something like that, or
So
somewhere around there. It's cold.
just that temperature differential, what like is that? Doesn't that sort of don't you have to then worry about structure and
Yep.
and then if you want something to be strong but not have as much mass, so what those are the kind of decisions that you're making.
Yep, exactly. And that's, again, goes right back to how critical should thermal engineering be, because when you get different materials together, you would get CTE mismatch, you get things that are going to expand more than others. What kind of structural stress does that put on the whole system as well? So, yep, it goes right back to that.
So that's the other then, and so my question was, what kind of modeling software are you using to sort of do this? Are you using sort of standard ANSYS Fluent kind of modeling?
We're using, I think, I'm trying to think. I think right now the program is, my project is using 5 different analysis software, I want to say. And that's just modeling software, because we also do have a gentleman who does all of his modeling in MATLAB. So he writes up all his own code even. So that's even separate from doing ones that have really nice GUIs and everything.
Right.
So some of the software we use is, we use Creo as our main modeling software. We use Thermal Desktop, which is an ANSYS software now as well. I know there's our fluid engineers using a software called Star CCM Plus, and that looks at the fluid flow and the heat transfer part of it. And there's another one that I can't remember the acronym. It's like GFSSP, and that actually looks at a thermal network and how the heat transfer is through that whole thermal network.
Right, and then you can do that in sort of modeling software. But when you're testing your hardware, what kind of test bed conditions are you? How are you creating the space? How are you creating outer space on Earth?
Sure. So NASA, almost every NASA center has their own what's called a TVAC lab. That's Thermal Environment and Testing Lab, and they are huge, giant vacuum chambers. Well, the sizes kind of depend. We have some that are just little bell jars even, that actually you can pump all of the, all in quotations, all of the atmosphere out of, that then has also ways you can heat or cool the internal surface of the chamber as well. So we will put hardware in whatever type of chamber it needs to fit in to get whatever type of environment we need. There's also some now vacuum chambers that are set up with lunar regolith simulant. So if you have a system you're going to send to the moon, you can actually put it in that vacuum chamber and simulate the lunar surface. So, yeah.
Yeah, and then this MARVL, this spacecraft you're working on, the goal is to put it into orbit around Mars. Do you think that your design, like what kind of design considerations would have to change if you were now trying to sort of land on Mars, like now make a Martian lander?
Okay. So the one thing that we have been discussing about is that the vehicle I'm working on would only be used for transportation. Once you get to Mars, there'll actually be another vehicle that will go back and forth between the surface. So yeah, so that's a little bit of difference there for what we're looking at.
Nice. And actually that then brought, while I was writing that down, not a question, I was like, ooh, is there anything that you saw on The Martian, which was kind of one of my favorite movies, that made you roll your eyes when you were watching it?
So usually when I like to watch science fiction movies, and my husband will be like, no, you don't do this, is I try to go, this is exciting. Let's see what they came up with. And I try to ignore everything else. But sometimes I just go, oh boy. But that's what I try to do, is just kind of be like a what if scenario. If everything is perfect in the world, or everything's not perfect in the world, what happens? So that's why I kind of address those. But yeah, there are some stuff where I go, oh boy.
Yeah. Well, and then I wanted to sort of get to the bi-wing, the bi-wing versus the quad wing
Yes.
configuration. So it was kind of interesting because not only are you getting the nice thing is that you can be kind of where that solar vector isn't hitting your wing, because the quad wing, there's no configuration in which one of the wings doesn't get that solar vector. So, but in the bi-wing, you can do that. So, what's the sort of savings that you get with the bi-wing versus the quad wing?
So I know let me see if I can get my slides. Whoop, let me get that out of the way. With that one, let's see if I can get back there to it. That there is a certain percentage of mass savings that we have in that setup.
Okay.
Let me see if I can find it. And I can't remember what the value is. Oh, wow, I have two versions of this presentation open. You think I'm super important or something.
Yeah,
How that happened.
yeah.
Let me see here, because I want to say it's 25%, but
Oh, that's right. Okay, yeah, I did see that number, but
yeah, right here.
Yeah, okay.
So you get about a 25% decrease in the radiator mass, and that's because you have an increased efficiency because you don't have all those view factor angles going on,
Right.
And it allows you to actually expel the equivalent amount based off of the quad wing, but the quad wing needs a whole lot more mass, a whole lot of surface area. So that's what we're looking at for that.
Okay. So another question that came in is, did the original space missions have to do so much heat shielding calculations? And were all these math models done the long way? Do you know from the original space missions?
I think they were done the long way because they didn't have all the technology, but at the same time, they didn't have all the technology. So the waste heat coming from the electronics found inside those capsules and everything probably was not as great as how much heat we generate now with our computers. So you can think of it that way too. So it was more about just keeping the astronauts a little more comfortable, from my understanding.
Right. We also have a comment in the chat that says, "I want the quad wing designs as it reminds me of the X-wing from Star Wars." Yes, but you've got to actually think that what came, like, this is a little bit of what came what is it? Art driving reality.
It is one of those where we're just like, oh, we're going to move from the quad wing, and it looks so cool though. So we're like, what can we do to make ours look so much cooler? So we're trying to get there.
Did you have to rely on any of your metal smithing? Did you try to do any of your metal smithing from your MFA to sort of to see this to model this out?
I haven't yet. I've thought about it, but I haven't yet. But I will say that my art degree, with all of that metal smithing and working with my hands, really helps me when we talk about, hey, do we need to consider, like, can we actually manufacture this? That has been exceptionally helpful in that area.
Yeah. Oh, yeah. Dina's loving that. Yeah.
So my suggestion, if you're in engineering, go do stuff with your hands because it will help you in the future.
Okay, and I think all the engineers on this call just had, like, we felt this warm glow inside our hearts. And then the other thing I do have a lot of questions. When you're modeling the flow in those fluid tubes, and now I'm going to sort of divulge that I'm an electrical engineer and a biomed, so this is the thing I'm pulling out from my transport phenomena class. So so bear with me over here. But do you model, because there's such a large differential temperature, which means that there's a large differential in pressure, which means that at some point you could maybe start with laminar flow, but somewhere it's going to get turbulent, right? I mean, because you've got just this huge amount of pressure and temperature differential. How do you deal with that? What do you deal with? How can you model it? Yeah.
The hard part is that I have a fluid engineer on my team so that I don't have to do it myself, kind of thing, because I'm in the heat transfer side. But I think that his Star CCM Plus software he uses, I think that takes care of it.
Okay.
So, but also the nice part though too is if you look at the part we're actually modeling, it's that heat pipe that's doing the sinusoidal type wave thing. And I bet I'd be surprised if there was actually like anything but turbulent flow going through that pipe. So, right.
Yeah. So the other thing is the pipe on the inside of that wing, is that also titanium? So is everything titanium? Because I was actually thinking one of the ways that you can stop that or damp out is just could you increase the compliance in your tubes to sort of help out, or have you, what is that made of?
There's a very interesting problem that we're dealing with, and that is that our liquid metal, which is sodium potassium NaC, it is not compatible with titanium from what we can see. So our heat pipes may be titanium, but our fluid loop is all stainless steel.
Oh, okay.
So,
but still quite still. I mean, quite solid. Like, have you considered using something other than a metal, like for the inside fluid lines?
Yeah, we haven't pursued that yet because the hard part is with the nuclear reactor. We have to be very careful about the other materials we use. So like any seals we have, they have to be metal seals because that gamma radiation, it'll kind of start breaking stuff down.
Yes.
So so that's when we have to really be careful about all our material selection. And I'll say material selection, I am so happy I took that class. So yes.
Yeah, that's great. I mean, I thank you. I got through all my questions, which is amazing. If we have any more questions, we still have a few minutes. If anyone has any more questions, I did see a lot of your professors on this.
Oh no.
Yes, yeah, yes. There's going to be a quick quiz for you.
Oh boy.
And if you fail, we take back our degree. No, I'm kidding.
Okay.
I'm kidding. I'm kidding. That does not happen. But thank you so much. This was amazing. And
I just put the link in again. Yes, definitely give us feedback. It doesn't have to be just Amanda's. It could be anything that you've seen so far today. Don't fill them out for things you haven't seen yet because there are other things coming up.
Yeah.
So wait on
I'm going to stop the recording if that's okay.
That's fine. Yeah.
Beautiful.
Right. So thank you so much.